Hey everybody, looks like we have an upcoming test on Unit 6 for Integrated Math 1 on exponential relationships. So exponential means that our variable x is in the exponent part. So exponential means exponential. So they graph J-curves when we get to that, okay? So here's an exponential function. We're gonna solve for x, okay? So what we need to do is get this 3 to the x all by itself. So I've got to get rid of, I'm sorry, I'm not solving for x. They want us to just plug in x equals -3. So we're going to plug x equal -3 right there. Okay, sorry about that. So when we do that, you guys, remember a number to a negative exponent, it goes downstairs in the denominator and becomes a positive exponent. So let's go ahead and do that. So here we have 4 over 3 to the positive 3, and then now we can do 3 to the positive 3 is 3 times 3 times 3, so we get that, so we get 4 over 27, okay? All right, so now this is exponential stuff, so that means this is going to give us a geometric sequence. So a geometric sequence, we need to figure out what's our rate of change, our r. So we just pick any two numbers. So we can pick 36 and -6, or we can pick -6 and 1. Anyway, so r is the right number divided by the left number. I like to call it righty divided by lefty. So to me, it's easier just to see 1 divided by -6 is going to be -1/6. Okay, so that's what r is. Okay, all right, and then our formula is our nth formula. It says write an explicit rule. So our explicit rule is a sub n. Some of our books call it f of n or t of n. Some books call it. I like a sub n. I don't know why. So it just means our nth rule right here. This is our nth term equals our first term times r. Well, we know what r is. It's this, -1/6 to the n minus 1. Well, our first term is this guy right here. So we're going to plug in 36 right here. We're going to plug in -1/6 right here, and bing, bang, boom, and that's our formula right there. Okay. All right. So now we can take that and we can plug in our 10th term, our 11th term. So if it said our 10th term, we plug in 10. And then 10 minus 1. Whoops, I'm so sorry. There should be a -1/6 right there. Man, I'm so bad on this. Okay, I make lots of mistakes. If you're in my class, you know that. I make lots of mistakes. There should be a -1/6 right there. All right, anyway, so just make sure that you have -1/6 because that's what r is, okay? All right, okay, let's get started. So write the next 3 terms of the sequence. Okay. So first of all, we have to figure out what is r, okay? So when we go to the right, it goes times r, times r, times r. If we go to the left, it goes divided by r, divided by r, divided by r. So looking at these numbers right here, I'm going to go righty divided by lefty, okay? So righty divided by lefty is going to get us 5 divided by 10 is 1/2. That's what r is. Okay, so all we have to do now is just multiply by half. So 20 times a half is 10. 10 times a half, yeah, I know, times a half is the same as dividing by r, is 5. And then 5 times a half, we're going to do 5 times a half is going to get us 5 halves. Okay, and then 5 halves times a half is going to get us 5 fourths. 5 fourths times a half is going to get us 5/8. Okay, so when we go to the right, we have to multiply by the r, and since r is a half, times a half, times a half, times a half. So here I multiplied all the numbers times a half right here, and they gave us all these numbers. So write the next 3 terms. Again, you have stuff just like this on your upcoming test. Okay, I made the test and for our school, and it's going to look just like this. Okay, so when a ball is dropped, the function f of x equals 15 times 1/2 to the x. It models the ball's height in feet after each bounce, where x is the bounce number. So to the nearest hundredth, that's 2 decimal places, because it goes tenths, hundredths. What is the height after the second bounce? Okay, so we're going to plug in 2. Okay, so 1/2 to the 2 power is going to get us, when we do a fraction to an exponent, then we square the numerator. So 1 squared is 2. 2 squared is 4. So we're going to end up 15 times 1/4 when we do that. Okay. And then 15 times 1/4 is like 15 over 1 times 1 over 4. So 15 times 1 is going to get us 15/4. And it says round it to the nearest hundredth, so it's going to get us about exactly 3.75 feet is going to be on that second bounce. Yeah, okay. All right, so the first term of a geometric sequence is 3, and the common ratio is 2. What is the fifth term of the sequence? Okay. All right, so here we have our nth term. Our nth term of a geometric sequence is always the first term times r to the n-1 power. Okay, all right. So here it says the first term is our a sub 1, so that's 3, and then r is 2, and we just got to plug in n equals 5. So it's just number crunching. Okay, so now we're going to do 2 to the 5th. So we have to do the exponent first. So 2 times 2 times 2, and 2 more. So 5 2s. Okay, 2 times 2 times 2 times 2. 5 times gets us 32, so 3 times 32 is 96, okay? All right, so here we go. We got an experiment is done studying the growth of a population of a rabbit farm. The function f of x equals 250 times 1.05 to the x represents the growth in the rabbit population, where x is measured in months. Okay, all right. So this 250 is always your starting point. So if it asks you what it's to start with, how many rabbits were initially in the rabbit farm, it's always this right here. So think about x is the measure in months. So after 0 months, there's 250 because 1.05 to the 0. Remember, anything to 0 is 1, so this would be 250 times 1. So how many rabbits were in the farm initially? Well, that's 250, okay? What's the growth rate? Well, the growth rate is this thing in parentheses right here. So 1.05 is what we're going to put right here. That's our growth rate right there, okay? And then after 3 months, how many rabbits are in the farm? So that just means we're going to plug in x equals 3 right here, f of x, and then we're going to be 250 times 1.05 to the third power. Okay, so if we plug that in our calculator, use our exponent feature, so it's going to be 250 times 1.157625. Okay, and then when we multiply that, we get that. So about how many rabbits is that? So let's round, you guys. That's going to be about 289 rabbits in a rabbit farm after that. Okay. All right, so determine the rate of change, which is r, in each geometric sequence. If it's not geometric, say so. Okay, so let's look at this guy right here, okay? So geometric means we're going to go times r, times r, times r. Can you see this is 1 times 3, 3 times 3, 9 times 3. Here r equals 3, okay? So in this next one, we got to go times r, times r, times r. So 5 times 2 is 10. 10 times 2 is not 15. This one's not geometric. This one's arithmetic from the first semester. 5 plus 5 is 10. 10 plus 5 is 15. So this one's not it's not geometric. That's what they want us to say right here. So it's arithmetic, but it's not geometric. Okay, let's look at this guy right here. Okay, so 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40, so that one is geometric, so that one is r equals 2. Okay, how about this one right here? Okay, when we go to the right, negative 5 times negative 3 is 15, 15 times negative 3 is 45, negative 45 times negative 3, remember a negative times a negative is 135, so r is negative 3 on that one. Okay, all right, so here we go. We solve for x. Okay, so this is what I was thinking at the very beginning of this lesson right here. Okay, we have to get this 3 to the x by itself, and here we have to get the 4 to the x by itself. So over here, I'm going to divide both sides by 5. Over here, I'm going to divide both sides by this 3 right here. Okay, so that's what that is right there. So when we do that, we get that, and then right here we have to change this number to a power. Over here, this number is going to be this number to a power. Okay, in IM3 we'll learn how to do other strategies, but for right now, when we get to this stage right here, that means 27 is 3 to a power. Okay, 3 times 3 is 9, 9 times 3 is 27, so this is 3 to the third. Okay, here 4 times 4 is 16, 16 times 4 is, here, let's do this, I know what I'll do. This one's, we can do this on the calculator right here. So I'm just, oops, I clicked the wrong one. Hopefully I can keep going with this. Here we go. So 4 times 4, here we go. 4 times 4 is 16, we know that. Okay, times 4, there's our third 4, is 64. Times 4, here's our fourth 4, that's going to get us 256, which is that. Okay, so that means this number right here is 4 to the fourth right there, so we did it 4 times. Okay, and then so now we got the same base on each side, so now we can set these exponents equal to each other. So right here, this exponent equals this exponent, x equals 3. This exponent equals this exponent, so x equals 4. Okay, so complete the table, graph the function, state the end behavior, and the y-intercept. Okay, so here we go. Okay, so we have y equals f of x. F of x equals -1/2. So let's complete the table. Okay, let's plug in these values right here. So I'm going to plug in -2 right here. Let's do that right there. Okay, so -1/2 to the -2 power is, flip that fraction. Okay, so that negative stays. Okay, the negative right here stays. We don't do anything with that negative. It's outside. It's not being included with the exponent. So 1/2 to the -2, flip the fraction, it becomes 2 over 1 to the +2. Okay, 2 over 1 to the +2 is 4, but it's -4 because of that negative. So when we graph that guy, we're going to go to the left 2, okay, to the left 2, and then down 4. Now just check out your graph, you guys. Okay, so the x-axis is going by 1s, and your y-axis is going by 2s. So we go over 2 squares and down 2 squares, because that'll be -2, -4. All right, let's plug in this value, -1. We're going to plug it in right there. So so it's going to be -1/2 to the -1. That's what I have next right there. Flip the fraction, it becomes 2 over 1 to the +1, but remember that negative's there, so we get -2. I don't know what just happened, it just moved a little bit. Anyways, and then so we get -1, -2. Okay, so when I graph that guy, go to the left 1 square because it's going by 1s, and go down 1 square because that's going by 2s. Okay, now exponential graphs always do the J curves, or the upside down J curves, or the backwards J curves, or whatever, or the upside down backwards J curves. And for now in integrated math 1, they're always asymptotically going towards the x-axis. Okay, when you get to integrated math 3, you're going to take them away from the x-axis, but it'll still go towards a horizontal asymptote. Horizontal is left and right. All right, let's go ahead and plug in 0 now. Sorry, you guys, I get off on a track right there. So 0, anything to the 0 is 1, but it's going to be -1. So we're going to graph 0, -1. Okay, that's right there. So 0, go down 1/2 square. Okay, so right here, we're going to go over 0 and then go down 1/2 square. Okay, let's plug in 1. Okay, so it's going to be -1/2 to the 1. Sorry about that. Which is -1/2. Okay, so we're going to go over 1. We're going to go over 1, down 1/2 square. So which is down 1/4 square, because each square represents 2. Okay, let's plug in 2 now. So we're going to plug in 2. So it's going to be 1/2 to the 2 power. Okay, so 1/2 to the 2 power is going to be 1 to the 2 power over 2 to the 2 power. When you do fractions to an exponent, you got to square the top. 1 squared is 1, 2 squared is 4, and it's negative, so it's -1/4. So we go over 2, down 1/4. Okay, so we get that. So there's our upside down backwards J curve right there. Okay, exponentials always do that. End behavior. Okay, end behavior is this, you guys. As we go to the left right here, when we go to the left, that says this, as x goes to negative infinity. As we're going to the left right here, this graph is going down, so that's why it says f of x goes to negative infinity. As we go to the right forever, when we go to the right, that means x goes to positive infinity. This graph is getting close to the x-axis asymptotically. It'll never cross it. It just gets infinitely close, so we're going to say it's going towards y equals 0. The x-axis is y equals 0. Okay, so remember, f of x is always our y stuff. So what happens when we go to the left? This is what happens to the graph. What happens when we go to the right? This is what happens to the graph. Okay, let's try another one here. So negative 3 times 2 to the x. Okay, so we're going to plug in these x values here again. I'm going to plug in x equals negative 2, negative 1, 0, 1, and 2 right here. Okay, remember a number to an exponent, we flip it, and to a negative exponent, we flip it, and it becomes a positive exponent. So 3 times negative 1 half, I'm sorry, 3 times 1 half squared is 1/4. So negative 3 times 1/4 is negative 3/4. So when we graph that, you guys, we're going to go over 2, over 2, because x equals negative 2, so negative 2, and then go down 3/4. Okay, remember each square represents 2, so half a square would be 1, so a little bit less than a half a square. Okay, we're just fudging right there. Okay, let's plug in negative 1 now. Okay, so we get negative 3 times 2 to the negative 1, which is negative 3 times 1 over 2 to the positive 1, which is negative 3/2, which is negative 1.5, not quite negative 2. Okay, so we're going to go to the left 1, down a square and a half. I'm sorry, down 1.5. Remember, 2 squares is 1 square is 2, so we're going to go down not quite 2. Okay, let's plug in 0. Okay, when we plug in 0, anything to the 0 equals 1, so negative 3 times 1 is going to get us negative 3. So there's negative 2, so negative 3 would be right there. So let's go ahead and plot that guy right there. Plug in 1. So 2 to the first is 2. Negative 3 times 2 is 6. 2 to the second is 4. Negative 3 times 4 is negative 12. Okay, did I say 6? Negative 6. Okay, do you see your upside down J curve? There it is right there. End behavior. Okay, so our end behavior again is when we go to the left, that would be when x goes to negative infinity. This graph is going towards the x-axis right here. So f of x would be approaching 0. When we go that way, that would be when x goes to positive infinity. This graph is going down, so it's going to negative infinity. Okay, the y-intercept is always where the graph crosses the x-axis, so where x equals 0, so 0, negative 3 would be our y-intercept. Okay, almost done. All right, so a pond has 550 fish and the population decreases 3% each day. Write a function to represent the number of fish after X number of days have passed. Okay, so the function is always going to be the first term, which is this guy right here, our initial population, times 1, because it's 100%, and then we take off or add. But this is decreasing, so we're going to take off the fish population, 0.03. Remember, it's 3%, you move the decimal 2 places to the left, so we got to insert a 0, so 0.03. Okay, so just think of 100 minus 3 is 97, so that's going to be 0.97 right there. So 550 times 0.97. Find the population after 7 days, so we're going to plug in x equals 7. So when we do that, we get that decimal, and we get about that, so about 444 fish, okay? Almost done, you guys. Emma has $1,800 in her savings account. Her savings account balance will increase by 10% each month. Now, this is such a fictitious problem because there's no way that we can find an account balance that will do that increase. But if you could, please jump on it, you guys. You guys will make some money. So write a function to represent how much money Emma will have in her savings account after X months. Okay, so X months. So we're going to do the 1,800 times 1 plus 0.10. Okay, so This is our initial amount, 1,800, and we always do 100% plus the increase because it's increasing, so it's going to be plus 0.10, so we get that, and so there's our function right there. And then so this next part says if right here, if no other deposits or withdrawals are made, so she just has her 1,800 bucks in there, how much money will be in the account after 1 year? So 1 year means 12 months, so I'm going to plug in 12 right there and right there. Okay, so we get that, and when we do that, we do 1.1 to the 12th power. So she's going to make, you can see that that's just out of control. If you can make $5,000 over that in a year, jump all over that. But that's not true. This is not a correct problem right there. It's a correct problem, but if you see that, please jump on it because you'd be rich. Anyways, hope you guys do well on your test, and take care.